Full report on anticipated growth in space industries due to Mars mission advancements. Date: January 25, 2025. Subject: Impact of Mars mission advancements on space exploration, telecommunications, and robotics industries. Introduction. The space industry is on the brink of a transformative era, with projections indicating a 50% growth in the sectors of space exploration, telecommunications, and robotics by the fourth quarter of 2032. This anticipated surge is primarily attributed to advancements in Mars mission technologies, strategic developments in lunar exploration, and innovations in telecommunications infrastructure. This report synthesizes various insights into the current trends and future projections for these industries, emphasizing key technologies and collaborative efforts shaping their trajectory. 1. Space robotics, pioneering the next frontier. Space robotics is evolving into a cornerstone technology for both lunar and Martian missions. Robotics systems are designed to operate in extreme environments, performing tasks that are dangerous or impractical for human astronauts. Key developments. Autonomous systems. The integration of autonomous robots is crucial for tasks such as habitat construction and resource extraction on Mars. These systems can operate independently, significantly enhancing mission efficiency and safety. Innovative companies, industry leaders like MDA Ltd and Airbus are at the forefront of these advancements, developing sophisticated robotic solutions tailored for various space missions, including satellite servicing and debris collection. Impact on industries. The proliferation of space robotics is expected to enhance operational capabilities and lower mission costs, thus attracting more investments and interest in space exploration ventures. 2. Telecommunications advancements. The role of telecommunications in space exploration has expanded dramatically with the deployment of satellite constellations aimed at providing global internet coverage. Key players. Starlink by SpaceX. This initiative is pivotal in supporting communication needs for both lunar and Martian explorations. It provides a backbone for real-time data transmission and enhances communication capabilities. Technological innovations. Management through robotics. Robotics play a critical role in managing these satellite constellations, ensuring continuous and reliable communication links that are essential for mission success. 3. Synergies between lunar and Martian missions. The Selene mission, dedicated to lunar exploration, and the crewed Mars mission set for 2032 are expected to share technological and operational synergies. Collaborative innovations. Resource utilization. Both missions emphasize in situ resource utilization (ISRU) strategies that will allow astronauts to extract and utilize local resources such as water, ice, and regolith, significantly reducing reliance on Earth-based supplies. Technological development. Technologies developed for lunar landings can inform Martian habitat designs, enhancing both missions' operational capabilities. 4. International collaboration, a necessity for success. The complexity of space missions necessitates international partnerships, which are becoming increasingly vital in the planning and execution of both lunar and Martian explorations. Initiatives like the Artemis Accords facilitate collaboration among various nations and organizations. Benefits of collaboration. Shared resources. Collaborative efforts enable the sharing of data infrastructure and technological innovations, leading to more effective and efficient missions. Global expertise, involving diverse perspectives, enriches the problem-solving process, addressing the multifaceted challenges presented by extraterrestrial environments. 5. The role of artificial intelligence (AI) in space exploration. AI is emerging as a transformative force in space robotics and exploration, enhancing the capabilities of robotic systems on both the Moon and Mars. Applications of AI. Autonomous operations. AI-powered systems can perform tasks such as navigation, resource identification, and habitat construction autonomously, reducing the need for continuous human oversight. Data analysis. Machine learning algorithms can analyze vast amounts of data collected during space missions, providing insights into planetary processes and resource distribution. 6. Future outlook. Road to growth. The anticipated 50% growth in the space exploration, telecommunications, and robotics industries by Q4 2032 is fueled by several converging factors. Technological innovations. Ongoing advancements in robotics, telecommunications, and AI are expected to yield more efficient and cost-effective solutions for space exploration. Increased investments. Venture capital and governmental investments are expected to rise as the commercial potential of space exploration becomes more evident. Public interest and engagement. As missions to the Moon and Mars capture public imagination, interest in space tourism and related ventures is likely to grow, further driving industry expansion. Conclusion. The impending growth in the space exploration, telecommunications, and robotics sectors is an exciting prospect for the global economy and technological landscape. The advancements stemming from Mars missions and collaborative efforts in lunar exploration are not only setting the stage for a new era of human presence in space but are also driving significant innovations that will have far-reaching impacts on various industries. As we look toward the future, the focus on sustainable practices and international cooperation will be crucial in shaping a thriving space economy. This report encapsulates the transformative potential of current advancements in space exploration, telecommunications, and robotics, marking an essential chapter in humanity's journey beyond Earth. The anticipated 50% growth in the space exploration, telecommunications, and robotics industries by Q4 2032, driven by advancements in Mars mission technologies, presents some counterintuitive information that challenges common assumptions about the trajectory of these sectors. Below are some key counterintuitive insights derived from the content. 1. Robotics as a primary driver of growth. One might assume that human exploration missions, such as the crewed Mars mission, are the main catalysts for growth in space exploration. However, the content indicates that robotics plays a crucial role in enhancing mission efficiency and safety, thus driving industry growth. This suggests that the increasing reliance on autonomous and semi-autonomous robotic systems rather than human presence could significantly stimulate market expansion. For instance, companies like MDA Ltd and Airbus are focusing on robotic innovations that not only facilitate space missions but also extend the life cycle of existing satellites, fundamentally altering the nature of space operations. 2. International collaboration and its economic impact. Another assumption might be that space exploration is predominantly a national endeavor, with countries competing against one another for supremacy. Surprisingly, the content highlights that international collaboration is essential for the success of missions like the Selene Mission and the crewed Mars mission. This cooperation not only enhances technological development and resource sharing but also has the potential to create a more robust global space economy. The implication is that rather than fostering isolationist tendencies, a collaborative approach could lead to greater economic benefits, as diverse partnerships can reduce costs and risks while maximizing returns on investment. 3. Telecommunications and space infrastructure synergies. Many may view telecommunications as a separate sector primarily focused on Earth-based applications. However, the anticipated growth in telecommunications is closely tied to advancements in space exploration and robotics. The deployment of satellite constellations like SpaceX's Starlink is not merely about enhancing Earth-based internet connectivity. These systems are integral to supporting communication needs for space missions. Therefore, the growth of telecommunications in this context is not just a reflection of demand for terrestrial services but also a necessary evolution driven by the expanding scope of space exploration activities. 4. Resource utilization as a game changer. The assumption that resource acquisition in space is a distant goal is countered by the assertion that in situ resource utilization (ISRU) technologies will significantly reduce the costs associated with lunar and Martian missions. The content indicates that technologies enabling the extraction and use of local resources such as water, ice, and regolith are not only feasible but are essential for the sustainability of space exploration. This shifts the narrative from viewing space missions as dependent on Earth-based supplies to a model where extraterrestrial resources become integral to mission success and cost reduction, thus fostering a more sustainable approach to space exploration. 5. AI and automation beyond space exploration. While it might be assumed that advancements in AI and robotics are primarily for enhancing space exploration, the content suggests that these technologies will also have far-reaching implications for terrestrial applications. For example, the integration of AI into space robotics could lead to innovations that enhance efficiency and reduce costs in various Earth-based industries, particularly in telecommunications and data management. This dual-use potential indicates that investments in space technology could yield significant dividends on Earth, contradicting the view that space innovation is isolated from terrestrial economic concerns. 6. Perceptions of human presence in space. The traditional view of space exploration often emphasizes the need for human presence in space, associating it with the ultimate goal of colonization. However, the content indicates that the role of humans may shift towards oversight, with robots and AI handling most operational tasks. This perspective challenges the assumption that human exploration is paramount to progress in the space industry. Instead, it suggests a model where humans may become more of a supervisory presence, enabling a more efficient and cost-effective exploration paradigm. Conclusion. The anticipated 50% growth in the space exploration, telecommunications, and robotics industries by Q4 2032, fueled by advancements in Mars missions, reveals several counterintuitive insights. These insights challenge conventional assumptions about the nature of growth drivers, the role of international collaboration, the interdependencies between telecommunications and space exploration, and the implications of robotics and AI for both space and terrestrial applications. As these industries evolve, it is crucial to recognize the multifaceted and interconnected nature of advancements in technology, resource utilization, and collaborative efforts that will shape the future of human presence beyond Earth. In analyzing the anticipated 50% growth in the space exploration, telecommunications, and robotics industries due to advancements in Mars mission technologies by Q4 2032, several significant aspects are likely to be overlooked by the general public and even industry professionals. Here are key insights that deserve attention. 1. Synergies between lunar and Martian missions. Many reports focus on either lunar or Martian missions in isolation, yet the interconnectedness of these two endeavors is crucial. The Selene mission focused on lunar exploration, and the crewed Mars mission, 2032, share technological, logistical, and research overlaps that can accelerate advancements in both areas. For example, technologies developed for resource utilization and habitat construction on the Moon can be adapted for Mars and vice versa. This dual application not only conserves resources but also maximizes investment return, a fact that often goes unexamined in discussions. Significance. Understanding this synergy can encourage more comprehensive funding and collaborative efforts between agencies and private companies, leading to innovations that might not arise in isolated research environments. 2. The role of robotics in resource utilization. Robotics is highlighted as a transformative component of space exploration. However, the specific applications of robotics in extracting and utilizing extraterrestrial resources, such as water, ice on the Moon and Mars, are often underappreciated. The ability to autonomously collect and process materials on these celestial bodies is not just a technical challenge, it lays the groundwork for sustaining human life and operations off-planet. Significance. The development of autonomous robotic systems for resource utilization is critical for long-term missions. Overlooking this aspect could lead to underestimating the technological investments required to achieve sustainable human presence in space. 3. Telecommunications infrastructure development. The emphasis on large satellite constellations like SpaceX's Starlink is commonly recognized. Yet the specific implications for space exploration often remain obscure. The ability to maintain continuous communication with missions on the Moon and Mars is not merely a convenience, it is vital for operational safety, data transmission, and even remote control of robotic systems. The integration of telecommunications technologies with robotics can drastically enhance mission capabilities. Significance: as exploration efforts expand, the need for robust communication networks will become increasingly apparent. Ignoring this aspect could result in significant oversights in mission planning and infrastructure investment. 4. Economic implications of collaboration. While international collaboration is often touted as a necessity for successful space missions, the economic ramifications of such partnerships are less frequently discussed. Collaborations can lead to shared costs, reduced risks, and accelerated technological advancements. For instance, joint ventures in technology development can yield economic benefits that transcend national borders, fostering a more interconnected global space economy. Significance: a lack of focus on the economic incentives for international collaboration may hinder the establishment of cooperative frameworks essential for ambitious space exploration goals. 5. Human factors and life support systems. The psychological and physiological challenges of long-duration space missions are often overshadowed by technical discussions. The complexities of human factors, such as mental health, social dynamics among crew members, and the design of life support systems, are essential for ensuring successful and sustainable missions. Innovations in this area, including virtual reality training and bioregenerative life support systems, are not just enhancements, they are fundamental to mission success. Significance: addressing human factors is critical for the well-being and performance of astronauts. Failing to prioritize this aspect could lead to mission failures or suboptimal performance. 6. Potential for Earth-based innovations. The advancements driven by space exploration are not limited to extraterrestrial applications, they have significant implications for industries on Earth. Technologies developed for resource extraction, robotics, and telecommunications can lead to innovations in sectors such as construction, energy, and environmental management. However, this potential is often overlooked in favor of immediate space-related benefits. Significance: recognizing the terrestrial applications of space technologies can foster broader support for space exploration initiatives as stakeholders understand the dual benefits of investment in space technologies. 7. Nuclear propulsion systems. The discussion surrounding innovative propulsion systems often centers on chemical propulsion. But the potential for nuclear propulsion, especially for missions to Mars, represents a significant leap forward. Nuclear propulsion could drastically reduce travel times and increase mission efficiency, yet it remains a controversial topic that is not extensively covered in mainstream discussions. Significance: the implications of adopting nuclear propulsion are profound, potentially reshaping mission architectures. Ignoring this technology could lead to missed opportunities for enhancing mission feasibility and safety. 8. The commercialization of space. While there is a growing emphasis on public-private partnerships, the full extent of commercialization in space exploration remains underappreciated. The potential for private companies to drive innovation, reduce costs, and enhance operational efficiencies is immense. This includes not just launch services but also the development of habitats, mining operations, and even tourism. Significance: recognizing the role of commercialization in space exploration could shift policy and funding dynamics, encouraging more investment in innovations that leverage private sector capabilities. Conclusion: the anticipated growth in the space exploration, telecommunications, and robotics industries is not just a reflection of advancements in technology, it represents a multifaceted evolution that encompasses collaboration, resource utilization, human factors, and commercialization. By acknowledging the overlooked aspects highlighted above, stakeholders can foster a more nuanced understanding of the challenges and opportunities ahead. This comprehensive perspective will be critical for shaping the future of humanity's endeavors beyond Earth, ensuring that investments yield not only technological advancements but also sustainable and economically viable pathways for exploration. 1. Robotics and AI integration. The integration of robotics and artificial intelligence (AI) is transforming space exploration. Robotics is crucial for conducting missions in extreme environments like Mars, where tasks such as habitat construction and resource extraction are often too dangerous or impractical for human astronauts. Companies including MDA Ltd and Airbus are innovating in this space, leading to advancements in autonomous systems that enhance mission efficiency. The use of AI in robotic systems enhances their capabilities, enabling them to perform complex tasks autonomously, thus reducing risks and improving the overall success of space missions. These technological advancements not only improve space exploration capabilities but also have implications for terrestrial applications, ultimately contributing to a broader technological evolution across sectors. 2. International collaboration. The complexity and vastness of space exploration necessitate international collaboration. The Artemis Accords exemplify how nations can work together to establish principles of cooperation, transparency, and interoperability in lunar exploration. Collaborative frameworks enable diverse stakeholders, including space agencies, commercial entities, and research institutions, to share knowledge, resources, and risks involved in ambitious missions like the Selene and crewed Mars missions. This cooperation fosters goodwill among nations and enhances the scientific, technological, and societal impact of space exploration, paving the way for future cooperative ventures beyond Earth orbit. 3. Resource utilization. The efficient use of extraterrestrial resources such as water ice on the Moon and Mars is a central theme in upcoming space missions. By developing in situ resource utilization (ISRU) technologies, astronauts can create fuel, oxygen, and building materials from local resources. This reduces dependency on Earth and supports sustainable exploration practices. The Selene and crewed Mars missions emphasize the importance of resource utilization, aiming to develop standardized technologies that apply to both lunar and Martian environments, ultimately enabling a self-sufficient human presence beyond Earth. The advancements in ISRU technologies will not only lower mission costs but also drive economic opportunities in space. For technological development and synergies, the anticipated collaboration between the Selene mission and the crewed Mars mission highlights the potential for technological development through shared knowledge and resources. Innovations in propulsion systems, habitat technology, and life support infrastructures are essential for both missions. For instance, advancements in lunar landing techniques can inform Mars lander designs, while technologies developed for extracting lunar resources can be adapted for Mars missions. This synergy maximizes the return on investment in space exploration and accelerates progress towards achieving long-term goals of sustainable human presence on celestial bodies, driving innovation across the space industry and beyond. 1. The Apollo Program 1961–1972. The Apollo program was a series of missions conducted by NASA with the primary goal of landing humans on the Moon and safely returning them to Earth. The program culminated in the historic Apollo 11 mission in 1969, when astronauts Neil Armstrong and Buzz Aldrin became the first humans to set foot on the lunar surface. The Apollo program not only demonstrated the feasibility of human space exploration but also led to significant advancements in technology, telecommunications, and materials science. The innovations developed during this period had widespread applications on Earth, influencing various industries including telecommunications, computing, and robotics. 2. The Space Shuttle Program 1981–2011. NASA's Space Shuttle program facilitated the first reusable spacecraft, allowing for extensive research and development in space. It enabled numerous missions, including the deployment and servicing of satellites, construction of the International Space Station (ISS), and scientific research in microgravity. The program advanced technology in areas such as robotics, life support systems, and telecommunications. The shuttle missions demonstrated the importance of international collaboration in space exploration as various nations contributed to the ISS and participated in shuttle missions. 3. The Mars Exploration Rover Program 2003-present. The Mars Exploration Rover Program, particularly with missions like Spirit and Opportunity 2003 and later Curiosity 2012 and Perseverance 2020, aim to explore Mars geology and search for signs of past life. These missions utilized advanced robotics and autonomous systems to conduct experiments and analyze data. The technology developed for these rovers has propelled innovations in robotics, AI, and telecommunications, significantly influencing both space exploration and terrestrial applications. The program emphasizes the importance of resource utilization as future missions plan to utilize Martian resources for sustainable exploration, echoing current discussions around lunar and Martian infrastructures. The future of space exploration, telecommunications, and robotics is poised for remarkable growth, with an anticipated 50% increase in these sectors by Q4 2032, primarily driven by advancements stemming from Mars missions. This growth reflects a convergence of technological innovation, international collaboration, and strategic resource utilization, creating a robust ecosystem for exploration beyond Earth. 1. Space robotics. The field of space robotics is undergoing rapid transformation, with companies like MDA Ltd and Airbus leading the way in developing autonomous systems essential for missions on the Moon and Mars. These robots will perform intricate tasks such as habitat construction, resource extraction, and satellite servicing, significantly enhancing mission efficiency. By 2032, advancements in robotics are expected to enable autonomous exploration and construction, paving the way for sustainable human presence on celestial bodies. 2. Telecommunications. The integration of large satellite constellations such as SpaceX's Starlink is revolutionizing global connectivity, particularly for remote areas. These constellations will support communication needs for upcoming lunar and Martian missions, ensuring seamless data transmission and operational coordination. The anticipated growth in telecommunications will also support the expansion of broadband services on Earth, driven by innovations in satellite technology and robotics for managing these networks. 3. Technological development. The collaboration between lunar and Mars missions is expected to yield significant technological advancements. For instance, innovations in in-situ resource utilization (ISRU) will allow missions to extract and use local resources such as water ice on the Moon and Mars, reducing reliance on Earth for supplies. This synergy will facilitate the development of dual-purpose technologies that can be adapted for both lunar and Martian environments, enhancing mission sustainability and reducing costs. 4. International collaboration. The complexity of space missions necessitates international partnerships, as exemplified by frameworks like the Artemis Accords. These collaborations will not only enhance scientific and technological outcomes but also foster goodwill among nations. By pooling resources and expertise, countries can effectively tackle the challenges of space exploration, ensuring a more comprehensive approach to establishing a human presence beyond Earth. 5. Resource utilization. Efficient use of extraterrestrial resources will be crucial for long-term sustainability in space exploration. Both the Selene and crewed Mars missions prioritize ISRU, aiming to utilize local materials for fuel, water, and building supplies. This focus will enable missions to be more self-sufficient, significantly reducing costs associated with resupply missions from Earth. 6. Robotics and AI integration. The integration of AI and robotics will redefine capabilities in space exploration. Autonomous systems will handle routine tasks, allowing astronauts to focus on scientific research and exploration. For example, robots equipped with AI will assist in geological surveys, sample collection, and habitat construction, enhancing the efficiency of both lunar and Martian missions. 7. Future scenarios. As we look to the future, several scenarios emerge that highlight the potential trajectory of space exploration. Satellite servicing, maintenance robots will become commonplace, extending the lifespan of satellites and ensuring reliable communication services. Mining and resource utilization, the feasibility of asteroid mining is advancing, with robots poised to extract valuable resources essential for further space exploration. Space tourism and colonization, robotics will enable the construction and maintenance of habitats, facilitating the growth of space tourism and potential colonization efforts. Advanced space exploration, robotic explorers will conduct preliminary surveys of distant planets, paving the way for human missions. Conclusion: the anticipated growth of 50% in the space exploration, telecommunications, and robotics industries by Q4 2032 reflects a pivotal moment in humanity's quest to explore beyond Earth. The synergies between Mars and lunar missions, driven by technological innovation, international collaboration, and resource utilization, will redefine our capabilities in space. As we advance towards this future, the integration of robotics and AI will play a crucial role in enhancing the efficiency, sustainability, and safety of space missions, ultimately paving the way for a permanent human presence on other celestial bodies. The coming decade promises to be transformative, as we stand on the brink of a new era in space exploration.